So this is a new concept. It's called calorimetry, and it's basically the study of heat associated with chemical and physical changes. And as mentioned before, we measure heat in a variety of ways with some different units, but let's define what we call a calorie. A calorie, and just underline that there, a calorie, is defined as the amount of heat energy needed to raise the temperature of 1 gram of water, so that's important, 1 gram of water at 1 degree Celsius. So 1 calorie equals the amount of energy needed to raise 1 gram of water 1 degree Celsius. And you've also heard of these things called calories in your food, and we'll call those dietary calories. And actually a dietary calorie is 1,000 regular chemistry calories or regular science calories. And notice the difference in the abbreviation here. Even though they're both called cal, one is a big C, so it means many, and then the other one is a small c. So capital CAL is a regular dietary calorie, and that is equal to 1,000 regular science calories. So don't get the two mixed up if you're looking at how many calories are in your food versus how many calories we need to raise the water thing. So the other concept that you have to remember, the other equation that's now becoming more of a prevalent, is this equation Q equals mc delta T. And you're going to be using this a lot in this chapter and from many chapters after this. And basically what it is Q is this is defined as the heat. So Q is our term for heat, and M, you know, M is mass, and then we have this new term here called specific heat capacity, and I'll talk a little bit about that in a second. And then there's this delta T, and delta T is always defined as the final temperature minus the initial temperature. So we could rewrite this as delta T equals T final minus T initial. And T final and T initial just start with, it's just relative to where the process starts. So T initial is the initial temperature where the process starts, and T final is the final temperature where the process ends up. And T final and T initial don't necessarily have to, T final does not necessarily have to be larger than T initial. And there could be a case where the final temperature is actually lower than the T initial. So delta T in this point would be, if you had T final lower than T initial, then delta T would be negative. So just keep that in mind. It's not an absolute value. It is actually a negative or positive depending on final versus initial temperature. And now let's talk a little bit about that heat capacity thing. This is the specific heat capacity. And heat capacity and specific heat capacity are slightly different. The specific heat capacity is the energy required to raise 1 gram 1 degree C. Once a substance 1 degree C. So it's the amount of energy required to raise 1 gram of substance 1 degree C. And as we mentioned before, if you look back over here, the calorie is defined as raising 1 gram of water 1 degree C, whereas the specific heat capacity is a general term where 1 gram of the substance, in this case for the substance would be water, 1 degree C. So all materials have different heat capacities, and so you'd have to understand what each heat capacity is before you do any type of heat calculations. So in general, for specifically for water, we have 2 heat capacities, and we're listing them right here. So this one is in joules, and there's 4.18 joules per gram degree C, and 4.18 joules also equals 1 small calorie, right? So you can see here that these are equivalent, right? The calorie is the unit to raise 1 gram of water 1 degree C, and 4.18 joules raises 1 gram of water 1 degree C. So those are equal. So these are equal. And then if the Q is minus, then we have an exothermic reaction. So remember that, exothermic. And that means, again, that the heat is being given away by the reaction or being lost by the chemical reaction. And then the endothermic reaction is we need to add heat to the reaction to get it go. So that means that Q is going to be positive, right? Q is going to be positive. And also, if endothermic reaction means that if you look at this equation here, that delta T, the final temperature, must be greater than the initial temperature, because there's no other thing in here that can be a negative. You can't have negative mass, and you can't have a negative heat capacity, but you can have a final temperature and initial temperature be opposite each other. So if Q is minus Q, excuse me, if Q is a minus or negative Q, then it's an exothermic reaction. And then if Q is positive, it's going to be an endothermic reaction. Okay, so let's look at a couple of examples of this Q equals MC delta T thing. So the first one we're going to walk through together, and I'm going to explain how we set it up. And then there are two problems on here that are going to be looking at different approaches or different things that you can calculate what the Q equals MC delta T formula equation. And then we can understand that we can solve for any of the variables as long as we have we can solve for any of the four variables as long as we have three of the variables known. So let's look at the first one here. So we have how many joules of heat are released when 72.5 grams of water at 95 degrees C cools to 28 degrees C. So we do know already that we were looking for how many joules, right? So that is our Q. We were looking for that, so that's our Q. And then we have 72.5 grams of water, right? So our grams of water is this material here. That's our grams. We can just put that's our M, right? And then we know our C, because we've given that one before, and this is our C value in our equation. So we'll put that C. And here's our delta T, and this is T final minus T initial. And then we'll have that to be equals delta T, right? So we know all the factors that we need to know to calculate Q. We know the mass, we know the specific heat, we know the delta T because we have the initial and final temperatures, so we should be able to solve this. And if you put in all these values here now and do the calculation correct, you should get the answer should be minus 20,300 joules, right? And so it should be fairly straightforward if you set up the equation this way. So let's look at another equation and try this one. So this one is asking you to calculate the specific heat capacity of gold if it requires 48 joules of heat to warm 25 grams of gold from 40 degrees C to 55 degrees C. All right, so let's look at how we set this up here, and let's try this together again. So we have we write our general equation. Again, always write the general equation so you understand what you're looking for, trying to solve for. We're going to make it a little bit bigger here so we have some room. All right. So Q equals MC delta T, and in this case we know what the Q is, right? Because that's our given 48 joules, so that'll be that value there. And then we know what the grams of gold is, because here's our grams here, so that'll be this value here. And then we know what delta T is. We're just going to circle that one here because we have both the final and initial temperature. So we're going from T initial, which is 40, to T final, which is 55. Right, so that'll be the delta T. So we have T, that delta T goes in there, T initial minus T final. So we have all the variables that we need. The only variable we're missing is this one, C. Right? So let's see how we can set that up. So let's erase some of this stuff. All right, erase this. So let's just erase this. And then let's go back to how we're going to set this up now. So let's put in our values now. So we already had our Q. So we have 48 joules equals, and then we know our mass, so we're going to have 25 grams. Let me make that a little bit bigger. Okay, 25 grams. 25 grams. And then we know we don't know our C, and then we know what our delta T is, right? And our delta T would be 55 minus 40, so that equals 15 degrees C, right? So so now we have these information, and we could rewrite this again to be 15. It's 48 joules equals 375, because that's over here, 375. That's C. And our answer here would be 0.128 joules per gram degree C. So that's our answer here. I'll erase the rest. So that's the answer to that one. 1.128 joules per gram degree C. And I'm going to move this up a little bit. And then our answer for here is 2300 joules equals 45 grams times 4.18 times delta T, which is T final minus T initial. That's 25. And the answer you would get for T final would be, 37.2 degrees C. That's T final. Okay, so here's another example of how you can try it. So you should try this one by yourself first using this same thing. I'll just give you a little hint again. So let's try this again. So we make sure we're going to use this type of equation, right? That's Q equals MC delta T. And then you should be able to figure out which one of these variables goes into each one of the variables that you have in the equation. So I'll let you try to work this out and get an answer, and I'll come back and help in a few minutes. So stop the video, work out the problem, or pause the video, work out the problem, and then when you're ready to look at the answer, hit play again. Okay, so you're back. So let's look at how we would set this up. So we have how much heat is needed to warm. So we know we're trying to find out what Q is. So that's our unknown, and we know what how much heat is needed. So let's go here. 4.377 grams is our M. So I'll put that grams, and then we're going to multiply that by C, and we're given C, which is 0.24 joules per gram degree C. So joules per gram degree C, and then that's going to be multiplied by some number here, which is going to be actually, if we do the number here, it's 27. Let's just going to put this down here. 27.5. That's the final. That's T final minus 25, and so that's T initial. That's initial temp. So we're going to have actually this is going to be 2.5 degrees C. So let's rewrite this over here to make this a little bit. We're going to rewrite this to make this a little better, so we have a little bit more room to work with. So a little bit more room to work with. Just make these erasers a little bigger. Okay, so let's put here. So we have again rewrite this. So we have we're looking for Q. So our mass was 4.37 grams times, and our specific heat is 0.24 joules per gram degree C times, and we said this was 2.5 degrees C. So our units will cancel. Think. And then we have basically 0.24, which is roughly a quarter, times 2.5, so that would be 0.75, right? And then we have 4.37 here, so the answer would be 2.6 joules. All right, so if you do the math here, that's what you get. So if you didn't get that, try to rework it again using the information that I just gave you. Okay, here's another problem that you should be able to do. Basically, in the same line, we're going to use that Q equals mc delta T equation to do this. And we're trying to find the specific heat of a substance, and then we're giving you the 1500 calories, 312 grams, and the delta T is going to be 15 degrees C. So stop the video here and try to do this on your own, and then come back in a few minutes and I will try to I will walk you through how it should be done. Okay, so let's look at how we're going to do this now. So again, we're going to just use the same basic equation, which is Q equals mc delta T, and let's define what we're looking for. We're looking for the specific heat, so this is the value we're going to be looking for in this particular instance. And we're giving all these other ones. We're given 312 grams. That'll be that. We have our delta T, which is going to be this value, and we're given our Q value, which is this value here. So let's just set that up over here. So we'll give ourselves some room here. So 1500 calories equals mass of that is 312 grams. We don't know delta C, so that we don't know what the C is, and then we have D is delta T is 15 degrees C. So we can rearrange this equation to do the following. We can rearrange this to say that C equals 1560 calories divided by 312 grams, and then times 15 degrees C. Right, that whole thing down there. And the way I did that is if you're just a little not weak, but a little less comfortable with math, is I just took this and I can divide this into this side, and I can also divide this into this side, and I'm only left with C there. So we can get rid of that again. So that's how I would set that up. But anyway, and I'll leave that to the reader to figure that out. But anyway, we have this. So we have C. So basically 1.560 divided by 312 is going to be roughly 5. And then we have 5 times 15 degrees divided by 15 degrees C, which is going to be this value here, 0.33 calories per gram degree C. So you should have got that if you did this correctly. And most materials are going to be less than water, so especially metals. Right. So one key thing that you could remember here is when you're looking at a bunch of answers is that if it's a metal, which it is here for, or it doesn't really say metal, does it? So all bets are off. So don't listen to me on that one. But if it's a metal, it's probably going to be less than 1 calorie per gram degree C, because metals are pretty good heat conductors, and so the specific heat is fairly low. But if it's not a metal, you're going to have to actually physically calculate it out and figure out what it is. Okay, in this one, we're going to actually use some scientific data to try and solve a specific heat capacity by experimentation. Now, we may not know what the specific heat of a metal is, but we do know that we can use that heat lost to warm up some water. And let's see how we set this up. We do know, first of all, we do know, or we should know, or we're going to be learning that Q of the water must equal Q of the metal in this case. All right, because the metal is going to cool down while the water is going to warm up. And since we assume that in this case that the system is not losing heat to the outside, so we assume that because that's just the way to model this, that the heat lost by the water must be, or the heat gained by the water. So this is water heat gained, so this is gained, and then the metal has lost heat. Then the two must be equal, right? Because we can't create or destroy energy. So if the heat gained by the water must equal the heat lost by the metal, because those are the only two things in the system, right? We have that sample. So knowing that, let's set up this problem and try to understand what we're doing here. So let's just do some things here. And okay, so first thing we're going to do is we need to calculate, set up the equation. So let's set up the equation. The 1,500 gram sample of water at copper at 100 degrees C is placed in 100 grams of water. So we have our 15 grams of sample. So let's just try the Q of copper first. So Q of copper equals, and then we're going to say 15 grams times specific heat, we don't know what that is, so that's going to be the C, times 100 degrees C initial minus final. So the final temperature is 25 degrees C. All right, 25 degrees C. The final temperature is 25.35 degrees C. And the copper started out at 100 degrees C. Right, so that'll give us that value. And that has to equal the Q of the water gained. Right, because the heat's coming from the water. The heat warming up the water must be coming from the heat lost by the copper. And then we can write that one down here, that the Q of the water equals, and then we have the 100 grams of water, so let's put that 100 grams. And we know the specific heat of water, so that's in this case it's 4.184 joules per gram degrees C. And then we know what the final, the initial temperature of the water was, 25, and you know the final, so that was going to be 25.35 minus 25 degrees C. So we have all the values there, and we can solve that and get the right answer. And let's look at how to do that. And the answer here, if you do the thing for C of the copper, which is this one we're solving for here, should be 0.13 joules per gram degrees C. And the hint here is, remember, we have to make sure that Q of the water equals Q of the metal lost. Right? Q of the water gained equals Q of the metal lost. And then we can solve our equation. So real quick here, what we want to be able to do is we want to understand what the mass of the cup is, the mass of the water, and all that. So if we have the mass of the cup and water, we can subtract that out, and we can get the mass of the water. We're going to be using this to calculate this out, and we're going to be saying that the mass of the water is 178.58, and I got that from subtracting this number from this number, right? Because this is the mass of the cup and water. This is the mass of the empty cup. So if you subtract out the cup, you should only get the water. And then the mass of the cup and water metal is that. So I get, if I subtract these two, this from, if I subtract this value here from this value here, then I get the mass of the metal is 600 grams. And then the rest of this we have here to thing. So we can calculate the delta T of the water, right? So the delta T of the water, we can calculate that. So delta T of the water is the final minus the initial. So the initial temperature of the water was this. So this is T initial for the water. And from T final, here's our final T. So this is T final. And then for the metal, I should change colors here to get not everybody confused. So let me switch that up here a second. So I don't want to get everybody confused of yellows and reds. So we use the red for the metal and the yellow for the water. So this is Ti for the water, and this is T final for the water. So the delta T between these two is 10 degrees C. And then this is T initial for the metal, and T final for the metal. And so the delta T for the metal is 52 minus 17, which is going to be 45. 52 minus 17 is actually not 45, it's going to be 35. So this is going to be 25 degrees C, so minus 25 degrees C. Okay, so now we have all our ingredients that we need to do to solve the equation. So we have our metal here, we have our metal mass, we have our water mass, we have our initial final temperature, or the delta T for our water, we have our delta T for our metal, and then the other thing we need is the specific heat of the water, and we do know that already. That's going to be 4.184. That's a given, we already know that. And the thing we're looking for is the heat capacity of the metal. So I'll solve it on the other page next door. Okay, so now we have our equation here. We know that, let's just remember what we did here. So delta T of the water was 10 degrees C. We know that the water weighed, the mass of the water was equal to 178 point, I believe it's 58 grams, but for whatever it's worth, it's close enough. And then the specific heat of water, which C equal to 4.18 joules per gram degree C. And then we'll do the other colors over here. So we know that. Okay, so our next is, now we can just put our metal one here. So we have our delta T of our metal is equal to 25 degrees C. Mass of our metal, so the mass was equal to 600 grams. And then specific heat, we don't know, that's our question mark. So let's set up the equation the way we know it now. So we have 178, and we're not going to worry about the units yet, we'll put them in a minute. 178 times 4.18 times 10 must equal, and then we'll go change colors here, 600 times C, which we don't know, times 25 degrees C. All right, so there we go. We set it up now, so we can see how both sets of the equations come together now. So I have the red equation for the metal and the yellow equation for the water, and now we can solve them together to get the answer for C. So let's rewrite this as we're going to rewrite this as a new equation in a different color. So I can just show you that no, we'll just do it with the same colors, right? Because we're solving for C. So C will equal 178.58 times 4.18 times 10, and then that will be divided by 600 times 25. Okay, does everybody see where I got that? This is from here, except for the C. All right, so the C is what we're solving for. So except for the C, let me just rewrite. Let me just do that again, so make sure everybody's clear about that. Let's just do that clear about that. So we're just going to erase that right there. Actually, I'm just going to erase this again and rewrite it so that everybody's clear about that. Sorry about that, folks. So 600 times C times 25 degrees. I will just leave it as, remember I said no units yet. So on the bottom here, we're going to divide by this and this together. That goes down here. And then our 4.18 times 10 is from this side of the equation, this side of the equation here, that goes here, right? And then we're left with C, right? So we're left with C here. Let me rewrite that a little bit neater. So remember, this is C equals, and then I'm going to rewrite this 178, and this is a 178 here. Okay, so you can see where everything comes from now, and then you can solve this for C, and therefore C will equal, so C equals 0.498 joules per gram degree C. So that should be your answer for that problem set. Okay? The answer to this one is plus 2,900 joules. The answer to this one is 37.89 degrees C. The answer to this one was approximately 265 joules per gram degree C. This one is approximately 15,050, 50 joules. This one is approximately 519.2 degrees C. This one is 85.4 degrees C. So there you have it, more extra problems. I didn't do the work on these. You should be able to do the work. If you didn't get the right answer, come see me and I can show you how to set it up.